So I'm going to talk a little bit about some of the innovations and advances in nuclear technology. Start off with a little background. You can read what that says. Log scales and quitters who can't find enough paper to make their point properly. But the fact remains that the potential for energy in nuclear is huge. With the resources that we have, if we utilize them properly, we have millennia worth of energy to power the world. But utilizing them properly is the key. Currently, we're just kind of running the nuclear fuel once through and then done, and that won't last us nearly as long, but the potential is huge. And this was recognized very early. There was huge optimism when nuclear power was first introduced. The first commercial reactor was Shippingport, and there was so much enthusiasm, a phrase often heard, that granted was mentioned towards fusion, but was applied towards fission as well, was, when this comes to pass, we'll have electricity too cheap to meter. And that was the real optimistic attitude. Down here on the bottom right, we see the actual installed megawatts electric of nuclear power as a function of time though. And you see that very enthusiastic period of time, and then it kind of levels off. You get to a point in time where it kind of slows down and enthusiasm wanes a little bit. So what happened? Why did that happen with such a promising technology? Well, a lot of factors played into this. There was politics. There was nervousness about the validity of safety for nuclear. There was the cost. As people thought about more things that could go wrong with the nuclear plant, and therefore more safeties against an accident in a nuclear plant, the cost went up very much so. Public relations. A lot of the times we find that the public isn't really well educated about what radiation it is, what it is, where it comes from, or how it impacts us in terms of our health and our lives. And that creates a fear because it's an unknown. And what I've heard it described as in the media is the silent killer. That doesn't make anybody excited about a power that produces a silent killer. So that's posed a real challenge. Another big and probably justifiable concern is the weapons proliferation. There's the way that we have decided to protect ourselves in the world against nuclear power is not restricting the knowledge of nuclear, but rather the materials for nuclear weapons. That's why we have the conflict and the discussion with Iran right now, is they're going through the steps that make it possible to enrich uranium to a level that you could make a nuclear weapon. And that's how we've decided to restrict that. Well, if you have nuclear power in abundance, the theory is that there's more opportunities for people to get their hands on that material, and therefore that's a major concern. And then, of course, there's the accidents. And so all of these, there's more than this. These are the ones that came to my mind immediately. But really, there's three major challenges at the heart of nuclear power that we are currently and have been trying to mitigate and solve. So I'll go through those next. First of all, very clear and apparent is the waste. So the problem with nuclear power is that as you generate electricity by fission, what happens is you not only generate the electricity, but you begin to generate other elements. As the neutrons are absorbed by uranium, and not fission, but rather transformed into plutonium or americium or curium, some of these other components, those things are radioactive for hundreds of thousands of years, most of which being plutonium. And so over here on this side of the plot, you see the relative radiological toxicity normalized to natural uranium ore. This is the goal, to get radiotoxicity here. Well, if you look at the time frame before standard nuclear fuel after it's put through the reactor, before it gets to the standard radiotoxicity, we're talking a huge amount of years. This is why there's such a big challenge with Yucca Mountain. The question that justifiably comes up regularly is, how do you know that you can engineer some type of system that can withstand the heat load, the radiation load, and not leak any of that waste for 100,000 years? We don't even have any buildings that have been around for that long. The pyramids are pushing the boundary of what we know. So that's a real concern. However, some of the work that we've done at Westinghouse looks at potentially taking out those dangerous components, the americium, the curium. They call them the transuranics, or TRUs, the trues. So if you were to take out just plutonium from this waste product, separate just the plutonium, which is very easy to do. There's a nitric acid separation process that's very well known and established. You would drop that time by an order of 10. Even better though, and one of the things that Westinghouse is really focusing on doing, if you can come up with a process to actually separate all of the trues, all the transuranics, and all you're left with is fission products. Those are the things, when the uranium splits, it splits into two different atoms, often different atoms. Those are called the fission products, and those are the ones that have a much shorter radioactive half-life. If you have just the fission products, you're left with only 300 years of radiotoxicity, and then it has no more danger to you than background natural uranium ore. So that's a much more realistic goal. There's some challenges associated with that, some of which I'll talk about in what do you do with the transuranics. So that's the first challenge that we're really trying to overcome that plagues nuclear. Is a lot of people said, well, we're not sure we want to invest in more until we know what to do with the leftover waste. Another big challenge, which hopefully he's not responsible for in real life, is the safety. The challenge with nuclear, unlike coal, natural gas, and the other electricity sources, it never actually completely shuts off, right? So you have this core generating 1,000 megawatts of, actually 3,000 megawatts of thermal heat, and 1,000 megawatts electric. You shut it down, and it drops immediately to about 6% of that output because all of the radioactivity that got started when you turned on the core is still going. So you have about 6% that decays exponentially until you get to about 1% after about 30 days. And 1% of 3,000 megawatts is still a whole lot of megawatts. And so there's a lot of heat that has to be removed. And the biggest problem we see with nuclear power and the worry about the meltdown is when there's no way to take that heat out. So the temperature builds and builds and builds until the cladding that contains the fuel actually melts. And the fuel, which is full of these radioactive fission products and trues, is then free to go anywhere. And one of the dangers that they worry about is the fact that it can be reconfigured in a critical configuration. In other words, you get this melted fuel that pools in the bottom, and there's enough of it there that it goes to critical again, and then you have a runaway reaction where you're getting more heat generated. And so that's one of the real challenges, and I'd say a vast majority of the safety work is dedicated to getting heat out of the reactor. That's kind of what happened at Fukushima. The earthquake happened, and they shut down the reactor safely, and everything was going to plan. They flipped on their diesel generators and started to circulate the water to keep this thing cool. But then the tsunami came, and it shut down the diesel generators. And with that particular design, there was then no way to remove the decay heat. So accidents is a major focus, especially when you're looking at reactors that you're going to keep operating for 60 plus years. That's a very long time to engineer to. And then the other challenge that came up is back when we were starting to build these things like crazy, both proponents and opponents of nuclear power started playing this what-if game. Well, what if this plant happened to get struck by an airplane? Well, what if this plant happened to get struck by a meteor? Some were more reasonable than others. But the challenge is you have these nuclear plants that you have to try and design a safety system that will work in all, or at least a vast majority, of these accident scenarios. In fact, Fukushima was designed to withstand an earthquake, but a smaller magnitude earthquake and not with the tsunami that followed. And so the what-if game, to some, did not go far enough. The challenge with that is the more what-if you play, the costlier the plant, because the more parts and the more complexity go into this nuclear reactor. And despite the best efforts, no matter how well you play that game, there's always going to be something unexpected. And so the challenge is to try and design even for the unexpected. And as we all know, every time there's an accident, whether or not there's damage, it really sours public opinion. For example, 3 Mile Island, there were no problems other than it cost a lot of money to the utility running that plant. There wasn't any deaths or problems, and yet it really soured back in the 80s the opinion of nuclear power. So the last part is the cost, and I touched a little bit about where part of the cost comes from. Because of the complexity, because safety is such a major issue, these plants cost billions of dollars. Now they return on that investment really nicely once you get them running, but that's a huge investment to put up front, especially for some of the smaller utilities that haven't run nuclear plants before. You tell them the price tag and they kind of look at you and say, okay, what does it really cost? It's a big amount of money, and oftentimes they've expressed that's kind of like selling the farm. They don't want to do that because it's a huge amount of risk that's not balanced in the rest of their portfolio. And so a lot of the focus in nuclear technology development, you can see this little diagram over here, is reducing the complexity and therefore the cost while still maintaining the same safety functions. So up here is the materials required in wiring and in piping and in space and valves for a typical light water reactor. And this is where Westinghouse managed to get to for each of these components for the AP1000. And that represents a substantial reduction in the capital cost. Another thing that has to be considered is the cost of public backlash when we do have an accident. For example, I'll use Fukushima. When Fukushima came out, the public came and insisted that we have even more stringent requirements for all the reactors in the US, even though they didn't face the same conditions as Fukushima. right? We have some of the reactors that are in the middle of Pennsylvania. If a tsunami gets there, we've got bigger issues than the nuclear weapon. So, but nonetheless, that backlash will affect everybody in a blanket statement. So that increases the cost of licensing and the challenge there. And finally, government has the capacity and has done so in the past to fund these reactor projects, but it tends to be fickle. Every 4 to 8 years, the direction changes, sometimes drastically, sometimes a little. So another thing that's happened is nuclear power has kind of got itself in a hole with the way trends have been going. So the economies of scale, the theory here is that the bigger the output, the cheaper per unit output it will be. So if you build a 300 megawatt reactor, it's going to cost this much. But if you build a 1,000 megawatt reactor, a lot of the scaling is not linear, and so it won't cost as much per unit. So we've been driving our nuclear plants to be huge. The first nuclear plant was much more reasonable size, closer to coal, 200 megawatts or so. But now we're looking at 1,100 megawatts is the Westinghouse reactor. Some of them in Europe are talking about making an 1,800 megawatt reactor. And that just makes for an even larger upfront payment. And that's very difficult, again, for these companies to manage. The other challenge, as I've mentioned, the cost of avoiding risk. What happens is the what-if game, they're trying to get rid of any risk of an accident. And what a lot of people don't realize is risk represents money. There's a cost to eliminating risk. And if you go to eliminate all risk, it's infinite money. Nobody will be able to afford anything that has no risk associated with it. So it's a game of balancing those risks. And so these are kind of questions and problems that we consider and put together as we're trying to develop nuclear technology that will be successful in the future. So I don't know if you guys have ever seen an actual reactor. This is an actual test reactor. I'm telling you, George Lucas had it right. The blue gull in his spaceships, that's exactly what nuclear looks like. They have that shrink off But, so there have been solutions to these problems that have been proposed for a very long time. And that is very large solutions, in other words, advanced reactor types. People have been looking at designing a reactor that overcomes or compensates for one or more of these problems. They've been around a while. The problem is some of them, when they were proposed back in the 50s and 60s, they didn't have the technology. Either the materials were lacking or the controllability in terms of process control was lacking. Where we're now starting to see the technology enter the area where we can actually make some of these reactors work. And they do a really good job of addressing one or more of these big three issues. Some of them have some fatal flaws. You've probably heard about sodium fast reactors. A lot of people are really enthusiastic about them. I'm enthusiastic till I remember that if you get a leak, there's a very big boom that's not related to the nuclear. It's the sodium exploding if you get it wet, and you're using steam to generate the power. And so some of them have some real challenges to cover. Another thing is they're expensive. It's first-of-a-kind technology that's never been done or proven. And the NRC is very good at focusing on keeping these things safe. But the flip side to that is that means they want as much data, as much experimentation, and as much modeling as possible, sometimes over the top, we feel. Regardless, that means it's very expensive to develop these models because every time we show them that we have 4 different CFD codes that say, hey, look, this is how the natural circulation is going to look, they say, yeah, that does look really good. Now build a test loop and test it. So you kind of have to dump a lot into these reactors to get them licensed for the first time. And that's a real challenge. And then similar to that, they're kind of paper reactors. They've never been built, some of them. And so on paper they look really good, but we don't know where some of the challenges are. And because of the costs associated with exploring those challenges, they're very slow to see that exploration and solution. So I'm going to go through some of them, some of these advanced reactors, and kind of the pros and the cons and what they're good at. So the sodium fast reactor I just mentioned, what it's good at? It burns waste. What happens is with the sodium fast reactor, you have neutrons that are at such a high speed that rather than just causing fission with uranium, they'll actually be absorbed by some of these transuranics, and the transuranics will transform into something either non-radioactive or that has a much shorter half-life. They call it transmutation. And so if you're in a fast reactor, because of the fast neutrons, or the high-energy neutrons, you can actually take some of the old waste and burn it up. So TerraPower is a company in Washington that is really focusing on developing and bringing to fruition a sodium fast reactor, where they are aiming to either A, mitigate the current waste supply, or B, you can actually use natural uranium. You don't have to enrich it, you just pull it straight out of the ground and put it in the reactor and it will run. A nice benefit is that it's atmospheric pressure. Light water reactors are pressurized, which means if you have a leak, things tend to explode outwards rather than going inwards, whereas you don't have that problem with sodium fast reactor. It has a huge thermal inertia. As you can see, the core is right down here, and it's in this big vat of sodium. And so the hot sodium basically comes out and up through the heat exchanger and then come down to the bottom, and then it's pumped through the pump in. There's so much sodium here that if you were to have an accident where you didn't have any type of cooling capabilities, it would take you a very, very long time to heat up that sodium. And because it doesn't boil at the same, it boils at a much higher temperature than water. And so theoretically, this reactor vessel gets to a very high temperature and will radiate the heat out long before you have those problems that you do with the water reactor because of the high temperature. So you can actually get rid of the decay heat if nothing is working. They call these a walk-away safe concept. The only flaw in that walk-away safety is the fact that it's sodium. So if you have a leak, it will burn in air or explode with water. That's completely wrong. There's not supposed to be a no there. Water and coolant do react. That's part of the problem. So some of the cons of this is the reactivity that I mentioned. It's also very expensive. US actually started building one of these reactors. We got about 83% of the way done before Congress said, you know, we don't have a stomach for this after all. It's costing a lot of money. Let's shut it down. Several countries have run them. Russia is the only one that currently still is running it, and successfully so. They have a reactor called the BN600, where they have been operating this reactor for some time, generating electricity and experimenting with waste burning. And then another con is the licensing because of some of the safety challenges. So another type of reactor. This one doesn't solve the waste problem near as effectively, but it is really nice because it's one of the first designs that was meltdown proof. So what do I mean by that? Well, the meltdown, as I mentioned, is when heat builds up in the core, it doesn't get taken away, and the fuel rods then melt, and you have no control over what happens to the uranium at that point on. Well, this fuel is in little pellets, about the size of the tip of a pencil, that are then put in these carbon graphite balls. And what happens is as the temperature increases, the graphite expands, and also the ability of the graphite to absorb neutrons goes up. And so as the temperature increases, suddenly there's not enough neutrons to be able to hit the other graphite pebbles, and it can't go critical anymore. And so it drops back down in temperature. So it kind of oscillates around this critical temperature and never reaches the point where it will actually melt down. And so this is a really innovative idea that really enhances the safety problem of you'll never have a problem not knowing where your fuel has gone. And that's what they mean by this meltdown proof. It's also very high quality. They're looking at temperatures of 1,000 degrees C. There's some materials challenges, but that's their goal and the capability in terms of the nuclear side of things. And also, the coolant is neutronically inert. You're not going to have helium getting activated. You're not going to have the helium causing absorption of neutrons and other problems like that. So the problems is it's very difficult to store the helium. There's a lot of leakage challenges. It's got a very low power density. It means it's going to be harder to pay these things off because for the same cost, you're generating less electricity or less heat in the core and therefore less electricity. Another real challenge, which you guys are probably familiar with, because it's helium, if you have an accident where air leaks into there, hot air and hot carbon do not make a good combination. The air ingress accident, if you get air in there, it's very likely that you'll get some serious fire started, and it's a real challenge to figure out how to mitigate that in terms of the safety world. Oh, and the other challenge is high pressure. So the molten salt reactor was one of my favorites for a while. This is a really weird design where the fuel is actually dissolved in the coolant. And so there's no solid anything. What happens is you have uranium in the coolant, which is a liquid salt floating around in here. Then when you get into the core, there's a bunch of graphite in there. And that graphite starts reflecting neutrons, and then suddenly there's enough neutrons that it goes critical. So only in here do you see the reaction, and then when the salt comes back out, it stops having that nuclear reaction. So even though the fuel is everywhere, you're only having the critical nuclear reaction inside there. Kind of a cool idea, because then what happens, you don't have the fission products building up. You don't have all that poison, that waste building up, because you can remove it in situ and store it in these tanks as needed. And so the waste problem becomes much easier to handle, rather than having a very expensive hot lab where you have to have 3 inches lead glass, or 3 feet lead glass shielding where you're working with these fuel rods. You just have to draw a little bit off the top and you're good. It's very simple to control. The challenge is when you put the uranium in these salts, it's very corrosive, and you have to use very expensive nickel-based materials in order to manage that. And also, because that uranium is flowing through the entire loop, even though it's not critical once it goes out of the reactor, it's still emitting neutrons and radiation, and so there's a high dose rate for the personnel in that reactor design. So that's one of the fatal flaws with that one, is there's a lot that has to be done for shielding outside of the reactor, which is very expensive. So another one. This is one that I think has the most promise now. DOE is showing a lot of interest in this reactor. This is the only one that's actually a new concept, and it's new because they hybridized a couple of the old ones. They took the molten salt concept of having a liquid salt, and then they took the high temperature gas reactor. So if you'll notice, it's a crummy picture, I know, but I couldn't get some of the other ones. The fuel is in the same pellets that's in the high temperature gas reactor right here, and the coolant flows down, around, and up through this area. Because it's in those pebbles, it has that meltdown-proof configuration, but it's not cooled by helium, so you don't have that air ingress possibility. It's cooled by liquid salt. Also, like the sodium reactor, it sits inside a vat, so you have a lot of thermal inertia. So this is a high-temperature reactor where you can get some very high-quality process heat, and at the same time, it's much safer because it has the same safety as a sodium fast reactor without really reactive coolant. And in fact, the Chinese are very interested in this reactor, and they're moving forward aggressively to start with this liquid salt reactor, and then hopefully, in their eyes, move towards the molten salt so they can solve their waste problem. So that's really where they're headed in that. And this was the subject of a $7.5 million grant by the DOE, and there's a follow-up grant this next year for another several $1 million to continue work on this. So there's a lot of promise and excitement over this liquid salt reactor. It can also be fueled by thorium. The advantage of thorium, I don't know if you guys have heard about thorium as a fuel. A lot of people are kind of excited about that. Thorium can be converted into a uranium isotope that is fissile. It will fissure, but it's lower on the table of elements, and so you're not as likely to get up into the transuranics that make really toxic waste. And so basically, you trade off a little bit of difficulty in fissioning the stuff in return for having a mitigated waste problem to some degree. So, next one is one that I worked on pretty closely at Westinghouse. So we talked about the challenge of having that huge chunk out of your wallet to build a $4 billion, $5 billion nuclear reactor that gets you a lot of money, but it's a lot up front. Well, one of the solutions to that was to build a small modular reactor. So this was kind of a challenge because remember that, that curve, that's economy of scale. If we were to just scale the reactor we had down to 225 megawatts, which is what this is, it would cost a lot of money. So what we had to do is we, in essence, had to find a new curve. In other words, we put in some new technology, some different stuff that cooled the reactor better so that it was on a different curve so that it could be smaller and a comparable price per megawatt to the larger reactors. One of the things that's done is instead of going out and building this on the site, they actually will build it in a factory. It's 12 feet in diameter, this reactor in here. It looks like a really long hot dog, I guess. But what that does, having it 12 feet in diameter only means you can rail ship it. You don't have to have specialized shipping and things like that. So you can build it in a factory, you ship it to site, and then it's much easier to fabricate. The studies indicate that it will be probably 1/7 of the time. Now, is it really that amount of time? I don't know. There's always a turbulence zone between theory and reality, and we'll see what happens with that. Some of the challenges, some of the technologies we've used. For example, we use passive cooling in this reactor, and so rather than having the pumps that Fukushima had, it's run by gravity. There's big tanks at the top, and if we lose power, those tanks will remove heat through a couple of heat exchangers for up to 7 days until the water all boils off. But that hasn't been proven, and so there's a lot of testing to be done and a lot of cost. When it's not a huge leap, it's the same technology, but here we're investing a lot of money to develop this technology that's, in the eyes of some of the people, a small step for the nuclear technology. And so that's kind of a roadblock, but there's a lot of excitement because it's a smaller size. Missouri in particular is very excited about having some of these down where they are for their Callaway site. And another challenge is there's still only 7 days of passive cooling there. And so the idea is to get it so it can cool itself passively forever, like the sodium fast reactor, but that's a real challenge when you have pressurized water in there. So those solutions have been around forever, but they're huge solutions that require billions of dollars to look at, to implement. So what goes on in nuclear research now? A lot of it is much smaller scale pieces that help bring about these large advanced reactors, right? So some of these things are like new fuel. I talked about that high temperature gas cooled reactor. Those pebbles that are meltdown proof was one of the innovations that was a small scale solution that people realized, hey, this is really good. We could use this for several types of reactors. So cross-cutting is the term that the DOE uses. They like to fund projects that are applicable over several different technologies and can benefit all of them, like new fuels, new cladding, or increased safety. Simplification, if you can make the same reactor have the same safety but have half as many systems, you're dropping the cost by a lot. So they like the possibility of doing those things. Another thing that's done is challenging the old safety approach. So when nuclear power was first built and people said, what if this? The answer was, I don't know, let's build more safety. Chink. What if this? I don't know, let's build this safety. Chink. And so they just build up a lot of safety systems, and rather than trying to evaluate the probability that something would happen and the severity of that accident, they really just put together more stuff and more stuff and more stuff till it became very expensive. So what's happening now is people are doing research to challenge, okay, so for that what if, let's do a probabilistic study. How often would it happen? What's the severity? They call it PRA, probability risk assessment. And by using that, they can actually cut the costs, maintain the safety, and uprate the current reactors that we have, because you can eliminate some of that unnecessary margin that's there. So really, the real progress that's being seen now is small stepwise innovations and progressions to make those fast and advanced reactor concepts possible. So an example of this is one of the things that I did with my research at MIT. The sodium fast reactors are very expensive, and so we thought, well, what if we can push more power out of this? So we looked at some annular fuel. Nobody likes when I throw up equations, so you don't have to look at that. But, typical fuel rods are the rods like this, where the coolant is on the outside, then you have the cladding, then you have a gap, then you have the fuel. And the temperature in the center of that fuel is quite high, because there's a very low thermal conductivity through the fuel, and that gap is a problem. Well, we made annular fuel that had the exact same amount of fuel, had the same ratio of fuel to coolant, and so it didn't mess up any of the neutronics. But now you have significantly more surface area for the cooling. What that did is it made it a lower peak temperature, so you can push up to 20% more power out of the same reactor, which means you get a better payoff, and it's a little more attractive in terms of payout for these people. Whoops. Don't do that. Another thing, simple. You guys are familiar, I think, with the pressure drop correlation. So you have water, or sodium in this case, that's flowing through this core full of long rod bundles. There's a significant pressure drop associated with that, and so you have to have even bigger natural circulation loops in order to push fluid through there if you need to cool the reactor. And so we looked at this pressure drop and realized that it's directly correlated with length to the square, or length directly proportional, but inversely proportional to the flow area, to the square. So in other words, if we lengthen this fuel rod a little bit in the gas plenum, in other words, the fission products that come out, some of them are gas, you have to have a plenum of so long in order to absorb those fission products. If we make that longer and thinner, then we'd actually see a 33% decrease in the pressure drop across the core. That means you're able to get more power out of it. You can build less pumps and systems to push fluid through there in an accident scenario. So in other words, you've just made the plant simpler. So very generically, we've talked about these things. What's the process for making these nuclear technologies happen? Well, what you have to do is you come up with the idea, the concept. In this case, it was the annular fuel. Then you have to create the model. In this case, we created a model that was similar to some experimental data so that we could validate it. And we modeled the rods, we modeled the neutronics, we modeled the heat transfer and the fluid transfer through this little mock assembly. And then we plotted it and verified it against the results for an experiment with the exact same conditions. So you think of the concept, you do a preliminary analysis in terms of your engineering toolbox, right? You do a quick, dirty hand calculation, and then you model it, and then you compare it to experiment. And that's exactly the process that needs to be followed for each of these things we've talked about to satisfy not just the NRC, but anybody who's investing in this technology. They want to know that it works, and this is a good foolproof way to verify that it will. So another thing that is happening just in this last year, people were so excited about the small modular reactor and how much safer they were. I didn't describe that, but because of the modular reactor, all of the piping and everything for the primary system is in here. There's no pipes that leave and go to these exchangers and then back in that could break. That's one of the real fears of current nuclear plants, is they have these big, we call them large bore pipes, 2 feet wide pipes, where if you break that, you're losing a lot of water really fast. They call it a LOCA, a loss of coolant accident. The integral reactor doesn't have any piping like that, and so they have a much, much simpler safety profile that they have to design to. So they wanted to try a large reactor. That's a real challenge because not everything scales linearly. So the small modular reactor that Westinghouse designed was about 12 feet wide and 89 feet high. It needed to be that high so you could have enough the surface area on the heat exchanger to create the boiling so that you can have the steam. Well, for the large modular reactor, you'd have to have 400 plus feet of these heat exchangers, and that makes a very large and upward reactor. Very easy to tip in an earthquake or anything like that. So you had to be kind of creative. We had to really go to compact heat exchangers and different designs that nobody has done before in nuclear. We actually don't boil inside of the reactor. Instead, what we do is we just have a heat exchanger, a compact heat exchanger. I don't know if you guys have heard of printed circuit heat exchangers. It's basically a bunch of plates, metal plates, and then they etch very small semicircular channels about 1 meter across in these plates, and then you stack them up on top of each other. So you have thousands of these channels that the water goes through, and it's designed to be a laminar flow heat exchanger that's very effective because it's surrounded by metal, and then you alternate hot and cold on the plates, and so it's very short heat transfer distance, and so it's a very effective heat exchanger. It can be very small, but it's unproven. It hasn't been used a lot. And it probably has some serious challenges because if you're boiling something in there, when you boil water, it leaves behind all of the impurities that are in it. You get deposition. If you only have a micrometer channel, you're going to be plugging that up real fast. So instead of boiling in the core, we decided to boil outside by basically having a flashing drum. We give up some on the thermal efficiency because when you flash the steam, you drop the temperature a bit, so the efficiency is lower. But the real payoff is capital cost is really decreased. So really a lot of these things are working on small changes to fix a problem here and there, where when you combine them together, you come up with a solution that can actually make these advanced reactors feasible. And that's our goal. Really, we want to see these advanced reactors come to fruition because they make nuclear power very attractive and very possible. And so some of the potential future work that the DOE is really looking at is they're looking at multidisciplinary design development. They want chemical engineers working with mechanical engineers, working with electrical engineers to come up with these solutions. Because you have to look at, well, when you're doing this boiling, is the stuff that's left behind going to corrode your fuel like crazy? Most of the work is not on the steady state nuclear reactor operation. That's simple and easy. It's all accident stuff. So you have to think of wild and crazy ways that this could go wrong, and then you have to fix it. You know, it's a funny game, but it's one that you have to play. And so they're really interested in also technology neutral. If you have a technology that will make all these types of reactors safe passively, they will go crazy over that. So a lot of money is being invested in people that can find ways to passively cool all of these reactor types. That's simple, rather than adding a whole bunch of different systems that are mechanically driven. And then also, they're looking for technology that's innovative beyond just nuclear. For example, one of the big things that's being studied right now is supercritical CO2 Brayton cycle. It has some really, really high efficiencies, upwards of 50% in some cases, and can be applied to other forms of heat generation, not just nuclear. And so several industries and labs and even universities have been really looking into the supercritical CO2 Brayton cycle. Silicon carbide, don't pay attention to the spelling, but silicon carbide is another example. It's a very, very strong material that's neutronically transparent, meaning it won't absorb neutrons or cause problems in that respect. But it also has applications for other areas because of its strength and resistance to the corrosion in this circumstance. And then advanced fuels. These are all kinds of things that really the DOE is looking to develop. And there's a lot of great opportunities because if we can get these to work, for example, silicon carbide clad, they've seen that you can have huge uprates in power if you can make that work. The challenge right now is how to fabricate it, how to make it. You can't do it using typical rolling and extruding methods that you use for typical stainless steel or zirconium clad. But if you had an idea, we put that together, you could work on that, and that would drastically change the field for these advanced reactors. Another thing is safer fuel. We talked about how the fuel melting is a big problem. Uranium oxide is ceramic, so it has a very low thermal conductivity. So when you don't have a cooling method, that heat builds up and it very rapidly melts. Well, looking at fuels that maybe have some increased thermal conductivity, that means they'll be able to get rid of their heat faster. You have more time to try and cope with an accident before you have a meltdown. And that's very, very desirable. The challenge with that is you have to find a fuel that not only has the better heat transfer properties, it's got to perform just as well or better with neutronics. Uranium silicide, I use this as an example because it does. It has more uranium for the same density than uranium oxide. And so you're going to get more power out of it, and it's got a higher thermal conductivity. There are some challenges. We don't have any or very much of some of the microstructure data. We don't know what it acts like when it's been irradiated for long periods of time. And so there's a lot of work to be done that can be done by all groups of people. Again, the field is really big into chemical engineers, mechanical engineers, electrical engineers, all work together because each one brings a portion of the problem to the table that can be useful. So, the biggest one, the one that they're most interested in, the holy grail, I'll say, of the nuclear industry is to have walkaway safety systems for all reactors. Some of them have that. Sodium is really good at that as long as it doesn't get wet. The high temperature salt reactor has that. But water does not, partly because you have pressurized water where if you get a leak, you're going to blow down and suddenly your core is uncovered and nothing is going to cool it. Currently, the top of the line light water reactor technology allows for 3 to 7 days of cooling without any action, without any electricity. So if Fukushima were to happen right now to one of these advanced passive reactors like the AP1000, you'd have 7 days where you were fully cooled before you really had to start thinking about what to do. Well, I guess before you had a solution. You're going to want a solution before the 7 days comes up. That's limited though. What they did to do this is they basically have a very large tank of water with a fail-open valve that when that accident occurs, it opens the valve and you start to get that water draining down, cooling on the outside and then some natural circulation cooling on the inside. But once that tank of water is out, you don't have any more cooling. That only lasts 3 to 7 days. You can't make it bigger because otherwise, you think about it, you have this huge tank of water, the bigger it gets, the bigger of a problem when you have an earthquake, because now you suddenly have this huge dead weight at the top of the reactor that's going to be breaking down and causing problems and causing more harm than good. And so one of the things that everybody's trying to figure out is how to make that happen. And I think there's some probably good ideas that people are looking at and exploring right now. For example, you guys are chemical engineers. There's a potential for using endothermic chemical reactions rather than a big tank of water that would last for longer than 30 days so that we could get some of that additional cooling. Some ideas like that. Maybe you could run a steam turbine to make things happen. And that's, a lot of people right now are pitching ideas to the DOE for how to make this cooling last forever without adding a terrible cost. You could make it happen right now, but it would cost you a lot with some of the ideas that have been proposed. So the idea is to keep it economical so we can still build these things, but to provide the safety. So that's really where nuclear safety is at right now. There's other potential cycles. I mentioned the cost cutting. There's a lot of interest in the cleanest cycle. That's water-ammonia mix instead of just water. And what happens is it's not isothermal when it boils, and so it actually increases in temperature, which allows you to have a higher efficiency. And therefore, 1 point of efficiency, if I remember right, equates to a couple $1 million a year in revenue for these plants. So getting more efficiency is a very big deal. If you can give a plant 10% additional efficiency, they're very, very happy with you. And so this is kind of where we're at. A lot of things that chemical engineers are very familiar with and very good at are what's needed to do this nuclear research. That's what surprised me when I went from the chemical engineering department at BYU into nuclear engineering. A lot of the people said, well, we can't really do this problem of hydrogen production because we don't know how to do the low energy value of hydrogen and the coupling with the nuclear plant. And I said, pick me. So there's a lot of opportunities for you guys to use your skills and your expertise to move forward with this nuclear technology. Aside from the neutronics aspect. That's certainly a part of it, but it's a small part relative to the things that need to be done. Because it's the most fun part, people have already done it. So now we get to do the dirty work and push forward the safety and the cost to where it needs to be. So, conclusions, there's definitely still a place for nuclear power in the U.S. energy plan. I hope that they see that there's still a place for U.S. technology in the energy plan. Large reactor solutions are possible, but they're not likely to be built in the near future in the US because of the cost, because of the licensing challenge. However, the rest of the world doesn't have a similar stigma, particularly China. They're moving forward building 140 reactors. So they say, we'll see what really happens. But they are moving forward actually building a salt reactor. They're actually building fast reactors. Russia already has operating fast reactors. Japan is no longer doing it after the last 3 years, which is understandable. But they, for a time, were doing fast reactors. The challenges are that industry can't justify the cost for the risk. If they spend $5 billion to develop this fast reactor and then 5 years from now it turns out nobody wants it, it's a huge risk that they're not quite willing to take because they've bet everything on it. The biggest potential, therefore, really resides in people like us getting together, coming up with innovative, cross-cutting technology that can be applied to these advanced reactors to make them reasonable, safe, and simple. So, it's kind of where nuclear sits right now. Any questions?
noticed at the end of your slide you talked about combining it with hybridizing it with other industries like solar. And what are some examples of how you can combine nuclear with other types of energy?
So the easiest example would be the hydrocarbon industry. You need a lot of process heat, you need a lot of steam. And it's possible, especially for some of these advanced reactors that have very high temperatures, to take the waste heat that's at 700 degrees centigrade and run them through to a energy plant to get that steam. So you're basically using the waste from one plant. One man's trash is another man's treasure, right? So you're hybridizing that by using that heat twice,
Okay.
and potentially improving the efficiency as it is. So, yeah.
Do you or does Westinghouse have an opinion on this traveling wave reactor that Bill Gates is promoting?
Yes, and they're in fact different. Westinghouse, at the moment, is we're a light water reactor. Light water reactors are the thing. They've been the thing forever. Admiral Rickover was a right kind of company. That's what they do. They do have a branch of research that I'm involved with that looks at these other things, but it's more for let's make sure nobody blindsides us with these technologies. If they get big, we want to buy them out kind of thing. My opinion is that the TerraPower group has the best chance of anybody to make it happen, honestly. They have really bright people that are being very clever in how they're doing testing. The fuel classification or qualification is very costly, time-consuming, expensive. And Kevin Weber works for TerraPower, and he has done amazing things. He's negotiated getting sodium fast reactor fuel assemblies that have already been used for 2 decades to do experimenting and testing to get the knowledge and qualification that they need. They have really bright people, and let's be honest, they have really deep pockets. For those of you that don't know, TerraPower is a brainchild of Bill Gates, indirectly, but still, they've got really deep pockets. They're looking to go to China, I suspect. They haven't publicly said that, but most of my classmates from MIT went there, and they've said, and they're looking at China to build first, because China is the one that's not over, well, China doesn't have the government problem. What they say happens. There's no debate, there's no litigation. That's good and bad. I prefer a free country, but that's a benefit. So, also, they have the funding for it. China's really interested in developing their energy infrastructure, and nuclear is definitely a part. Fukushima gave them a pause, but recently they've declared that they are still moving full bore ahead on nuclear, and so that commitment, I think, is appealing. Yeah.
What's the story on Germany's attitudes?
I don't know. I think they're silly, and they've had brownouts and challenges since, and they've talked about increasing price, and they still are having this attitude of we want to get away from nuclear. I think it's a lot political. I think that the political leaders get popularity for taking that stance. So I can't answer that other than with my own opinions, like I just did. So I think they're nuts.
What is the timetable on these smaller, more modular reactors?
So it depends on who you talk to. Westinghouse has said that they are going to turn in the design control document, which is a 70,000-page document describing every aspect of this plant. You think I'm kidding about complexity? That's what the licensing requires. They're scheduled to turn that in next year, midway through the year. After that, it'll be 5 years. Actually, it'll probably be more like 7 years until the first core is loaded. So we're looking 2020-ish. Other people say it's going to be, BMW is another competitor. They actually received $120 million from the Department of Energy to develop their small modular reactor. We bid for the same money and lost at Westinghouse. But they are bidding the same time frame, but a little bit earlier, because that was a requirement to get that funding, is to say a little bit earlier time frame than what we were saying. So all of them are going to be somewhere in the 2020 to 2030 time frame. And the reason for that is, even though it's not very different, if you make any small change in the fuel for a nuclear reactor, because that's what could be the danger zone, they want you, the NRC wants you to re-qualify the fuel, which means you have to do additional testing, additional modeling with all these different models, and so it takes a lot of time. Any little change makes a lot of time, which is why people really like these big changes, because you're really getting payouts by huge benefits rather than the small and steady. Unfortunately, you still have to do the small and steady to make those big things work. Yeah.
So how do you make your money? It takes so long. I mean, what are you
So
doing right now?
that's a good question. That was the most interesting thing for me, to see the funding structure for nuclear. A lot of the times, when you have a customer, when you get a customer, it's different from a customer somewhere else where they pay you and life is good. You actually try and get customers while you're still developing it. So we went around and tried to get customers while we're still developing the SMR, and then we say to them, you want to be the first customer? Why don't you fork over some of the money to help pay for this? So that's where some of the money comes. A lot of Westinghouse's money comes from servicing plants. That's their bread and butter. They go out, they do the refueling. They are the only ones who make leak-proof fuel. All fuel rods have a little bit of leaking, or have in the past, but Westinghouse now has no leaker fuel assemblies that haven't leaked at all in their entire lifetime of operation. And so they go out and they sell the fuel, they service the plants, they do maintenance, all those kinds of things. And then huge amounts of money come in when you sell a plant. When we sold an AP1000, the company went gangbuster celebrations because all of a sudden we had $4 billion come into the company per reactor that we sold. So it's kind of feast or famine. It's a very happy day when we sell one. But the cost structure is very different because oftentimes we're leveraging partners and even customers to cost share. And then relying on the government as well. Like I said, we applied for that small reactor funding. They have a second round coming out any day now. It's due out September, so we'll see when it actually happens. But I mean, there's opportunities for funding share from the government, and you really have to be creative. It's almost like bootstrapping a company, even though you're a large company, to get the funding, because it's a lot of money to make these things happen. So, does that answer your question? Yeah.
What would you say is the key research area to get the liquid salt reactors? Because I imagine that timeline is more close to 30 years or so. So what would you say is the most pivotal research area that needs to be figured out?
Well, let me amend your question and say the biggest area, not the research area. The biggest area is the licensing. They don't have a way to license a salt reactor in the US. They have extensive codes for licensing light water reactors. They don't know how to do that. So what is actually happening right now is the DOE and NRC and industry together are getting together and saying, okay, so how do we build a licensing framework, a structure where we can determine if these are safe or not? And it's a big endeavor. The licensing code is pages and pages and pages of requirements and even more pages of interpretation of those requirements. So the biggest thing that's needed is coming up with that regulatory licensing structure, a pathway to licensing. So hopefully that happens soon because they've started focusing on it in the DOE and NRC. So not as appealing as the research. Other research that needs to happen is some of the extreme accidents need to be defined, thought of. The what-if game needs to happen, and then we need to come up with solutions that are cheap and simple for it.
Okay, let's thank Dr. Mehmet one more time.